I'd like to welcome all our participants in the third session of our today's lecture series. Right now we are in Microfluidics track. We have with us Professor Shubhashish Majumdar, Heritage Institute of Technology, India. I would like to request our Honorable VC Sir to say few words for our speaker. Sir?
So I'd like to thank Professor Shubhashish Majumdar for giving his time to deliver the lecture in this faculty development program. So I have not personally met Professor Majumdar earlier, but I hope to interact with him in the future so that we can do some joint collaborative works and so on. So I'd like to thank you once again. And we have had a number of already very interesting sessions on microfluidic biochips earlier, and it is a very nice way to take a round off this track by your talk, where you'd be talking on again some optimization in the preparation of samples, possibly using some simulation techniques. So the participants, including and also us, we are eagerly waiting to hear from you, Professor Majumdar. Thank you again.
Thank you, Honorable VC sir. Yeah, we never directly talked to each other, but actually we met, I think, in a syllabus committee meeting of MacOut, which you.
Right.
Yeah, and
Right. That time I was with IIT Kharagpur. Yeah, from
right. And I think I saw you many times from a distance in VLSI conferences, which I used to attend earlier.
Okay.
And I think many
Yes.
of your colleagues and
Maybe I missed you during that
Madam
time.
Deepanita also used to attend. Okay.
Yes.
Yeah, I think, yeah. So we have probably common collaborators, common co-authors. Like I used to publish with Professor Vishwani Agarwal, and I think your
Which one? Yeah.
yeah, you have also published. Yeah. Thanks for the offer for collaboration. I mean, from a great researcher like you. Thank you.
Thank you,
Yeah.
sir.
Thanks to Dr. Banerjee for inviting me. Thanks to all the FDP participants, honorable academics, and if there is anybody from industry, I don't know.
Sir,
Thanks to all for joining. May I start the talk now? I think it is
sir,
2:30 already. Yeah.
I would like to request you that before you start the talk, I want to introduce you to all of our participants. May I, sir?
Okay.
Thank you very much, sir.
Okay.
So,
Yeah, so let's have a brief introduction. I am
sure.
Shubhashish Majumdar. I have been working.
Sir, I would like to introduce you, sir.
Oh,
Please,
that's great.
please
Thank you.
give me
I'm
this
sorry.
opportunity, sir.
Please.
Uh, So, Professor Shubhashish Majumdar received his MTech degree in Computer Science from Indian Statistical Institute and got his PhD degree in Computer Science and Engineering from Jadavpur University, Kolkata. He also worked as a research assistant in the Computer Engineering Department of Rutgers University, USA for a year. After finishing his undergraduate work in the Electronics and Telecommunication Engineering Department of the Jadavpur University, Kolkata in 1993, he started his career in Texas Instruments India Private Limited and has got over 7 years of industry experience. He has led product development teams working on innovative cutting edge technologies and has the experience of working as the technology head of a medium sized IT company. In 2003, he had shifted to full time academics and is presently serving as a full professor and head in the CSE department of Heritage Institute of Technology, Kolkata. He is also the Dean of UG programs at HIT. He has over 50 publications in international conferences as well as archival journals. His areas of interest in research include graph algorithms, physical design algorithms, algorithmic microfluidics, algorithms for social networking, and empirical software engineering. He has been awarded an award for excellence in the category of outstanding research accomplishment at HIT in 2016. He was also an NTS Scholar 1987 awarded by NCERT India. In 2006, he had founded a small knowledge-based IT firm named Dista Technologies that focused on niche projects requiring algorithm-intensive programming techniques. His key contributions there were some fast and efficient scheduling algorithms based on which the key projects evolved. Thank you, sir. Now it is over to you.
Thank you for such a nice introduction and the longest possible introduction, actually. Okay. I actually didn't mention even my designation in this slide because I wanted to save time. But anyway, thanks a lot. Okay.
Thank you,
Okay.
sir. Please.
Yeah. Okay. So it's a sultry afternoon, very high humidity, and all of you are from lunch. So I guess all of you must be feeling sleepy. And the good thing that probably you had a yoga session, which is also very close to my heart. So I guess you will not feel that sleepy because of that yoga session. But I will try to make it interesting for the next 1.5 hours. Maybe cutting a few jokes which may be a little out of the place, but that's the way I present. So let's see. So these are my collaborators, Dr. Nilina Bera, assistant professor in my department. So she was one of the PhD students. In fact, she is the second PhD student who graduated working under me. And here is Professor Dr. Bhargav B. Bhattacharya. He is my PhD guide in ISI. And I did my master's thesis and PhD thesis both with him. Now, the question is, how were they involved? Okay, Dr. Nilina Bere, obviously, the PhD student did all the hard work. And Professor Bhargav B. Bhattacharya, he guided us through this research. Then what I was doing, as usual, the middlemen, they don't do any work, but they talk a lot. Okay. And well, nowadays it's days of social networking. So, the terms betweenness and closeness and all those things. Maybe I am acting as a broker between two social nodes where I have maybe some betweenness value. That's why I am in the research. Anyway, so I first thought that the way I wrote the abstract, that I will start talking on simulation, and then I will talk on weighted dilution. But later on, I thought that since a little bit of extra time is available, typically the talks when you present a paper is around 30 minutes. Here it is around 1.5 hours. So maybe I can go in a way little unconventional, where I actually tell you how the research happened. Okay. So let's have a look at these points. You have already attended a few talks by very eminent scholars in microfluidics, and everybody, I think, talked about very efficient algorithms, how better those algorithms are. And I am going to talk in a slightly different way. I'm going to talk, we are not forming any new algorithm, but we are going to show how simulation can be used successfully in this domain. Okay. And maybe it's in line with my industry experience, where you actually think how to do things very easily without doing a lot of research. So I have worked for 7 years in the industry and then a long career in academics, and I have seen both the worlds, and the two together try to achieve the same thing, but in slightly different ways. In academics, we look for nice proofs, nice ideas, nice mathematics, so that when you write a paper, the counterpart will not say this is all trivial. And the industry target is how can I achieve new things with my old expertise, possibly not investing any big funds. Okay, so we always try to see whether we can use the present knowledge to do something new. And I'm saying have a look at these few points why simulation is being used. So when I started working in this one, I asked Bhargavda what to do, and he said a couple of things. He said about error analysis, and possibly a new algorithm can be formulated. I looked at the problem and I saw that all of you have seen that the denominator in a balanced dilution is typically 2 to the power of 10. Means you think about 10 balanced steps to generate a fraction. And I asked myself, how big is this problem? It looks like very small, right? The input size is very small. All of you must have an algorithm background and must have done an algorithm course. Even if you didn't do, these are very basic things. Like if the input to a problem n is only 10, then you actually can do exact simulation. Okay. If you look at the last bullet in my slide, it is somewhat like using an exact algorithm for some NP-hard problem when we are sure that the input size is going to be quite small. So this is the first thing that we teach when we go into the approximation algorithm chapter. So if you are an algorithm teacher, you finish the NP completeness chapter, and when you go to the approximation algorithm chapter, you actually say that, okay, the problem is NP hard, but you still have to solve the problem. And what are the 3 or 4 few ways how you solve the problem? And this is one of the solution. If you know beforehand that the problem size is going to be very small, you as well may use an exponential algorithm for an exact solution. If not, then you go for heuristics or approximation algorithm. Okay. Now, also there were other things that I noted. The problem actually requires to optimize multiple things, like number of steps to generate the fraction, the number of waste droplets, you always want to minimize this, the number of sample droplets, you also want to minimize that. You want the result generated by using probably zero investment. Okay, all we human beings are like that, especially the salespeople. Okay, or rather especially the people at the top of the company, they want zero investment and maximum output. Okay, but anyway, what we actually try to do is we will generate the output, but we want to use minimum number of sample droplets, likewise minimum number of buffer droplets. Now I noted that a single algorithm cannot achieve all at the same time. That's not possible. So I thought, let's use simulation. Okay, so computers are fast these days thanks to Moore's law operating for several decades. You know, I had a B degree from in electronics, so I will keep maybe going back to my electronics basics. So I talked about Moore's law. Now, so this is the scenario. So this is the reason I thought about simulation and told my student to focus on that. But that is all the justification I actually accumulated in support of my research. But how actually the research progressed? Why did we not go ahead to discover another new dilution algorithm? Well, in a way we did, but it is based on exhaustive simulation. The idea of simulation probably got latched because we started working with weighted dilution. Now, so the first question that needs to be answered is, what is weighted dilution? Now, most of the algorithms as a part of this FDP, or if you have done research in microfluidics, you see that we mix 2 droplets of equal of different concentration but equal size, 1:1. Then we mix, so the concentration gets somewhere in between, actually exactly at the arithmetic mean of the 2 concentrations, and then we split and we get 2 droplets of a different concentration. Then we keep on mixing droplets like this, but the droplet sizes are always the same. Okay, that is the important characteristics of balanced dilution. But we thought, let's go ahead with weighted dilution. So what is a weighted dilution? It's basically a generalized scheme for mixing to generate a target fraction. Means you take, say, one droplet of buffer and two droplets of the sample and mix them. And once you mix them and then you split them, you get three droplets of a concentration which is one third. Means if this is 0 and that is, say, that has a concentration, say, 1, then the resulting concentration will be one third. Or if you mix two droplets of buffer, so if you mix two droplets of buffer and one droplet of sample, then you get a concentration of 1/3. And if you take one droplet of buffer and two droplets of sample, then you get a sample concentration of 2/3. Okay. Now the technology is not quite ready yet to handle any general K/L mix. That means you will take one concentration of, say, 37% for 5 droplets, and then you take 3 droplets of another concentration, say 74, then mix and get a new concentration. No, the technology is not yet ready to handle that. But technology is progressing to handle the simplest type of weighted dilution, which is 1:2 or 2:1. Okay. Okay. So let's have some small figures. You see, I have a concentration C1, you have a concentration CH, sorry, this is CL and this is CH. And what I do is I take one droplet of buffer and two droplet of sample. So this is what is going to happen. This CL into 1x plus CH into 2x divided by 3x. For brevity, I actually cancelled out the x portion. And you get basically two-third of the concentration of the sample, which is CH. And also I already said this, if you took two buffer and one sample. Yeah.
Sir?
Yeah.
Sir, sorry to interrupt. Can you please hide the share bar, this top of the screen?
Okay, great.
It will
It is
be
coming to
helpful
you
for-
also. I'm sorry.
Yes.
Yeah.
Thank you so much, sir. Please continue, sir.
Okay, so thank you. Please keep giving me feedback, okay? Because I am like looking at a single big slide and not even seeing your faces or eyeballs, okay? So it's very difficult to actually talk in this mode. Anyway, thank you. Okay, so so you see Cl and Ch, and if I used two droplets of Cl and one droplet of Ch, then the resultant would be closer to Cl, and it is at the 1/3 point, okay? What is the physical structure which can generate this? There are two ways. So here you see you have a big droplet here. Initially, all the electrodes have a charge of 0 or a potential of 0. Then you make them 1. They get split, and then you pull it by making it 0 and 1. So the current will pull it here, and you have 3 droplets, each of the same concentration, but it depends on when you mixed what are each of these concentrations. When you mixed which was 2 and which was 1, it depends on that what is the final concentration. So how to split one 3x droplet into 3 1x droplets on a pathway mixer? This is a T-type orthogonal pattern on a 2D rectangular electrode array. Okay, so T-type pattern. Now this one actually causes some volumetric error. When you split, there is a chance that this particular bubble will have a plus epsilon portion, and then this will have a minus epsilon portion, or each of them has a minus epsilon by 2 portion, something like that. A little better way to do this is this, where you have three scales here, three pathways here, where all of them are at 120 degree. And all of you must have done this problem sometime in mechanics when you went from +2 stage to your degree college. So this is a symmetrical portion, and if I pull in, all these 3 will be pulled in equal direction. Because of the symmetry of the structure, the chance of volumetric error is much less. Okay, and the physics is, if you look at the left side, this is x cos theta, or f cos theta in this side. F cos theta, since this is 120 degrees, so it is going to be cos of 60 degree, and cos of 60 degree is half. So twice f cos theta will actually generate again fr. So ultimately what will happen, the resultant force due to these two to the left is same as exactly this. So ultimately you will get one here, one there, and one there. Okay. Okay. This tends to minimize the volumetric imbalance during splitting of a 3x droplet into three 1x droplets. Now there goes the electrical considerations, and those are actually the basic things. But what I am going to say is the first thing, that is our contribution. So the first question that I am asking is, can we generate all the fractions between 0 and 1 with denominator 3 to the power k, if I am ready to do k number of weighted dilutions of 2:1 or 1:2 type. Now it can come to your mind, why did nobody tell this when you are doing balanced dilution? Did they give a proof that all fractions can be generated from 1/2 to the power k to 2 to the power k minus 1/2 to the power k? To make it simple, suppose k is 4, 2 to the power 4 is 16, and you want to generate all the fractions from 1 to 15, and can you do it? Well, you have learned these new algorithms like BS, binary split, and then DMRW, which is from Indian Statistical Institute, then a number of algorithms from Taiwan. Okay, none of them gave such a proof because it was quite obvious, they thought. And but when I started thinking, so you see, I have written those things. The answer is yes, but we require a formal proof. Why? We did not bother about proving such a thing for balanced dilution when the denominator was 2 to the power k. Now I will give you the answer. Let's, instead of doing a 1:2, let's go to 3:1 or 1:3 mixed split. Okay. So what is going to be the denominator? Denominator is obviously going to be 1 plus 3/4. Now I am asking you a question. Can you generate the fraction half? Basically 2/4 or 8/16, because you know, if you mix 3 droplets of buffer and 1 droplet of sample, what will you get is a final concentration of 1/4. 3 into 0 plus 1 divided by 3 plus 1. And if you mix 1 droplet of sample and 1 droplets of buffer and 3 droplet of sample, then you get 3 divided by 4. But can I generate the fraction half from 1/4 and 3/4? You will immediately say, sir, I will mix 1/4 and 3/4 and then split it and I will get half. Yes, but remember, you are using a balanced dilution. You are mixing 1 droplet of 1/4 and 1 droplet of 3/4 and getting that. But the question I asked is, can you get all the fractions by using only this type of mixed split operations, 1:3 and 3:1? And the answer is no. If you go ahead and generate all these things, I mean, this is trivial, but I will still go through all the line because it will help for you to realize how the simulation is going on. It's very simple, but once we will give the details. So you say I had 0/4 and 4/4, the buffer and the sample. You get in the first step 1/4 and 3/4. Now blindly, like a machine, keep on doing 0 and 1/4. You get 1/16, 3/16. Believe me, these are correct, or you can actually do them yourself. 0/4 and 3/4, you get these two. 1/4 and 3/4, you get these two. 1/4 and 4/4, you get these two. 3/4 and 4/4, you get these two. And these are actually all the options I have listed down. What is missing rather? Or rather, how many have we missed? We could not generate 2/16, we could not generate 5/16, we could not generate 8/16, we could not generate 11/16, we could not generate 14/16. Okay. So we may now agree that we need a proof for 2:1 or 1:2 also. Is it okay? Can I hear some voices? Do you agree with this?
Yes.
Okay, so actually, you know, this is a little bit like a puzzle which we did when we were children. Like in our times, there was something called Anando Mela and Shuktara. But in Anandamala, these puzzles used to come like you are given some currencies. Can you generate all the values from 1 to 100? And then you will see earlier what notes we had: 100, then 50, then 20, then 10, then 5, then 2, then 1. They are actually the optimal way of generating the currency, so that you can generate all values like rupees 77, rupees 63, rupees 29 using only with those many number of currencies. So this problem has little similarity or analogy with that. Okay, now I give the proof for 1:2 and 2:1. Any number of any numerator x in the interval 0, 1, 2 up to 3 to the power k with denominator 3 to the power k can be generated in a maximum of k steps. That means I will do k dilutions, each of 1:2, 2:1 type. Look, I am not going to mix any balanced dilution here. Every dilution is going to be 1:2 or 2:1 type. And I am going to generate all the fractions. And I am going to show you how this can be done. Okay. The proof is by induction on k. The basis step is very simple. I need to generate x equal to 1 and x equal to 2, 1/3 and 2/3. And I have already shown you that it can be done, right? So you mix 2:1, you get 1/3. You mix 1:2, you get 2/3. Now, all of you know induction proof. You have a, okay, I'm going to give you the details induction proof 2 slides from here. Okay, 2 slides from here. I'm just going through the animation. So this is my induction step. Assume that all the fractions from 1 to 1 by 3 to the power k minus 1 to 3 to the power k minus 1 minus 1. So why am I doing this? Because 0 is already there and 3 to the power k minus 1 divided by 3 to the power k minus 1 is already there. That is 1. Okay. And I am assuming that all these intermediate fractions can be generated with the denominator 3 to the power k minus 1. They are available. And from there I am going to prove that all the intermediate fractions with denominator 3 to the power k, all the fractions with denominator 3 to the power k can be generated by using just one more step, one more 2:1 or 1:2 step. So let's illustrate this now with an example for k equal to 2. So it's very simple. Maybe all of you are very intelligent and you don't need this. But when I first proved it, I needed to make myself go in a formal way. So I'm saying, see, step 1, you do a 1:2. Okay. So now because we are going to do 2 steps, I have named the fractions as 0/9 and 9/9. Because you know, once we do 2 steps, below we have 3 square, which is 9 is the denominator. Now once I do one step of 1:2, I get 6/9, and then with 6/9 as the lower bound and upper bound as 9/9, and using 1:2 or 2:1, I can generate 7/9 and 8/9. Very simple. 6 into 2 is 12 plus 9 is 21 divided by 3 is 7. 6 into 1 is 6 plus 9 into 2 is 18. 18 plus 6 is 24 divided by 3 is 8. So I got them. Okay. What else I do? If the first step was 2:1, then I got 3/9. Then again using 1:2 or 2:1, I can easily generate these 2 fractions. Okay. Now the third one, with 1:2, I have 2:1. See here, after 1:2, I have this 6/9, right? And then with further, so after 1:2, I have 6/9, and then you do a 2:1, means 2, 0 and 1, 6. Okay, so 2 into 2 is 0 and 1 into 6 is how much? 2 into 1 into 6 is so I'm sorry, I did a mistake. So okay, so 2:1 and 1 is so if you do 2 into 0 and 1 into 6, you get 6 divided by 9. Sorry, you get I'm sorry, you get, just a sec. So 3 into 9 is 27 and 6 by 27 is 1 by 9. No, just follow this. Okay, so with 1:2 we got 6 by 9. Okay, then do a 2:1. So 2 into 0 plus 6, and in between you have am I doing any mistake? I think I wrote the reverse. Okay, let me go to the general proof now. Now have a look at the outline of the proof. Note that we already have, since I have 1 by 3 to the power k minus 1 to 3 to the power k minus 1 minus 1. If you just multiply both numerator and denominator by 3, you have 3 by 3 to the power k, 6 by 3 to the power k, up to 3 to the power k minus 1 into 3 is 3 to the power k minus 3 divided by 3 to the power k. So you already have these fractions. Okay, all you have to do is, between any two consecutive fractions, you have to use 2:1 and 1:2 to get all these fractions. Okay, that is the generalized proof. So basically you get, if you take 3r and 3r plus 1, if you do a 2 into 3r plus 1, 3r plus 1, and if you do a 1 into 3r plus 2 into 3r plus 1, you can generate all the fractions. Okay, okay. So given that I can generate all fractions by 2:1 and 1:2, we still thought that we still have a problem, but I'm going to tell that why I go for a hybrid scheme. But let's compare how this is getting done. Let's compare weighted dilution with balanced dilution. On the left, I show bit scanning. Those of you who are from microfluidics, you know very well how this is done. Okay, but those who are maybe you are just attending this talk. Okay, just have a look what is happening. 5 is 0 1 0 1. Okay, I will give other bit scanning examples later in a bigger example where you exactly understand. Actually what they do, these ones in the binary number, they signify how they are pulling from the sample, and these zeros, they are saying how they are pulling from 0. See what is happening in bit scanning. We mix 0 and 16 balanced, we get the numerator 8. Okay, then I mix the buffer and this concentration 8 to get 4. Okay, then I mix the sample and and this concentration 4. So 4 plus 16 is 20, divided by 2 is 10. Okay, and then I mix 10 plus buffer, I get 5. So actually I need 4 steps. Okay, sorry, so I need 4 steps to get 5 by 16, this concentration, obviously, because 2 to the power 4 is 16. What do I do in weighted dilution? Let's see. Suppose I want to generate 5 by 18. Okay, look what am I doing. I am mixing up balanced and weighted. So the first step is a balanced one, 1:1, 0 and 18, I get 9. Then I take a buffer twice, 2 droplets of buffer, 1 droplet of concentration 9. So I get 3, right? I get a concentration of 3. I mean, you do the maths, it's very easy. Now I take 2 droplets of concentration, 3 numerator, 3 by 18 as numerator, and 9 by 18 as denominator, and I will get 5. Okay, so 3 to 6 is 3 into 2 is 6 plus 9 is 15, and you divide by 3, you get 5. Okay, so you get 5 by 18. So this is the way, actually, compared to BS in weighted dilution, the fractions are getting generated. But now note, why did I use one balanced dilution here after giving the proof? Because, you know, as I said, weighted dilutions are costly in terms of the technology, because, you know, you have to use a different type of mixer which is costly, and it might take a little bit of more energy because you need more number of electrodes to be made positive, and weighted dilution are costly operation. Okay, so if I say that okay, I will mix some balanced and some weighted to generate a hybrid way of generating fractions, that will be less in terms of cost, but we are going to get the benefits of weighted dilution, which I am going to talk next. The benefit is already there. If you have a look, the number of samples droplets used here is 2. See how many times I pulled from the sample? 2 times. Number of buffer droplets pulled is 3. See 1, 2 and 3. Now what happened? How many droplets I generated of concentration 5? They are 2. So what happened? There was one droplet that was wasted here. There was one droplet that was wasted here. There was one droplet that wasted here. Why? Because I wanted a concentration 5 by 16. Okay. But I did not need 8 by 16. I did not need 4 by 16. I did not need 10 by 16. So they are wastes. So I have three waste droplets. Okay. Here in weighted dilution, I got a sample of 1, buffer of 3 I used up, but my waste was only 1 droplet of concentration 3, and I got 3 droplets of concentration 5 by 18, which was my target. Now obviously we are researchers. The immediate thing that will come to your mind, is this a coincidence? Is this a coincidence that the number of waste droplets were less in case of weighted dilution? What would happen if for other fractions it's the other way? I am obviously going to give you all that data. So we go for a hybrid approach using balanced and weighted dilution together, and this is the process we are going to follow. I'm going to stop here for about 30 seconds for any possible questions. Am I making sense? If you have any intermediate questions, you can ask me now.
Hello, sir. I'm very new to this field. I mean, I don't do research on this, but I'm curious to know a couple of things. So this mixing, when you are talking about, with respect to a pathological test, this happens for different kinds of chemicals that you mix and do the sampling.
Yeah, it can happen for pathological test. Yes, I mean some days maybe the number of droplets that will be collected by the technicians from your house for your T3 T4 TSH testing is going to be only 2 to 3 droplets instead of 5 cc or 10 cc. It is possible. Okay, right now you can think like in the chemistry lab you used to prepare different concentrations from samples and buffers. You are simulating that in terms of droplets.
Okay, and just one more thing, that whenever you are doing a computer simulation and getting a result, how close you are going with when you are going with a chip, real chip?
Okay, we have as a part of this thesis by Nilina, we have a very detailed work done in error analysis. Okay, but unfortunately, I won't be covering that today, as I said in the abstract, because I need to do all this preliminary work before I can go into error analysis. If time
Absolutely.
permits today, I will tell a little bit about that. But my presentation actually has the references for all the papers that we published. If you are interested, you can go and have a look at that, and later on send me email if you have any questions. Okay.
Definitely. Thank you so much, sir.
Okay. Yeah. I mean, see exactly what happens in case of a chip. You never know, because it's a highly complicated process with nanoscale technologies, right? Even in VLSI, I don't know. Even if you are a person from VLSI, I mean, I'm a person from VLSI. But when we do a stuck fault analysis, okay, or a delay fault analysis, actually we do very high level assumptions in terms of testing. But even those high level assumptions let us go to a very long extent in modeling the actual faults that are happening. You
Yeah,
understand?
device to device variation is a huge thing. I
Right,
understand
right,
that.
right. But you can actually still think of that. Suppose your TV is going wrong. Okay, so many things can happen at the electron level or diffusion level and with the diodes and all. but the mechanic, he actually taps certain outputs and can understand what is going on here, and what can be done. So we also do the analysis that way. We have a simplistic assumption that when I have mixed two droplets, and when I split them, if there is an unequal split, then one will have a plus epsilon and another will have a minus epsilon, and then we go a long way analyzing what happens to that plus epsilon and what happens to that minus epsilon as we go down the steps. Okay, sometimes it can be shown that that error gets magnified, and sometimes we can see that that error gets nullified after a few operations. That is very interesting. Unless you do an exact simulation with hand a few steps, you will not believe how that it can happen. Okay, but all those are there in details in the paper and also in the thesis. So if you are interested, you can read that. Okay.
Okay, sure, sir. Thank you so much.
Okay. Great. Now okay, now so what do I see? We saw that already, that using a maximum number of R mixing steps, it is possible to generate any integral numerator between 0 and 3 to the power R with D equal to 3 to the power R. But what did I say? I said that no, weighted dilutions are too costly. You cannot use too many of them. I will rather allow you to do use a number of balanced dilutions and a few weighted dilutions, and let's see whether you can generate the fractions that way. And we can actually give a proof that if you mix 1:1 and 1:2 or 2:1 dilutions, suppose let me take a small example and then I can come back. So you see this 432. Okay, how did 432 came? I said there are 4 balanced steps. So what is the denominator? 2 to the power 4, which is 60. Okay, and there are, let's see, there are 3 weighted steps. So what is the denominator due to that? 3 to the power 3, which is 27. If you multiply 16 and 27, you get 42. You have 432. You have to believe me. Okay, now the result is, using these two type of mixing, 1:1, 1:2, and 2:1, you can actually generate all the fractions from 0 to 432 by you, but it can be generated. Okay, and now so let me do a little bit of generalized calculation. Given the maximum number of balanced steps B and weighted steps W, the denominator is obviously 2 to the power B into 3 to the power W. By weighted, I mean 2:1 and 1:2 only, nothing greater than that. Okay, the number of total steps possible is B plus W, which is T. Initial lower numerator is 0. Initial upper numerator is D. Goal is to achieve all the fractions with numerators within 1 to D minus 1 using 1:1 and or 1:2 or 2:1 mixing steps using simulation efficiently. So I basically gave a formal definition of the, I basically, it's given you a formal problem formulation. Okay. Now, so again, very simple thing. Use 4 balanced steps and there's another example is so I said there will be 4 balanced steps and 3 weighted steps in the at the maximum. If you want to generate a fraction 217, I need 4 balanced and 3 weighted steps. 405, I need just 4 balanced steps. 399, I need 4 balanced and 2 weighted steps. You understand it is very difficult to check right now whether I am telling right and wrong. You have to work that out in your pen and paper. But one example I will go through so that you can check. Okay. So, oh, how did I miss that? I have an example. Maybe it's much later. Just a sec. Let me see whether I collected so many slides together. Yeah, so no, this is a entirely weighted steps 5/18. No, sorry, not weighted step. Yes, this is good. This is a balanced and weighted step. So have a look. 18 means I have 1 balanced step and 2 weighted step, right? 2 weighted step means 3 square, and 3 square multiplied by 2 is 18. Inputs are 0 by 18, 18 by 18. See here, I do a 1:2, I get 6. Because I use 2 buffers, the result is pulled towards the buffer, so it is 6 by 18. If I use the other way, it would be 12 by 18. Now, what do? I use 6 by 18 and I use 0 by 18. I use a balance step, 1:1. I get 3 by 18, right? Between exactly equidistant from 0 and 6. And then I use one droplet from 3 by 18 and two droplets of 6 by 18. And what I get is 5 by 18. Why? You see, 6 into 2, 12, plus 3, 15, divided by 3 is 5 by 18. So this is a typical way to generate a particular concentration using a mix of balanced and weighted steps. Now there are harder things after that, but let me go back. Now what I'm going to do is I'm going to give a motivation that using weighted steps makes sense. Because if you are doing a research and you need to publish paper, you have to motivate the reviewer that yes, what you are doing is making sense. Like I need to motivate you, why are you wasting 2 hours now with me? Unless it is motivated, then it doesn't make sense. Okay, so let's see. This is what we did. If you have a look, this is what I did. I said, okay, let's see. If you use 10 balance steps, the denominator is 1024. If you used 9 balanced and 1 weighted step, the denominator is 2 to the power 9 into 3 to the power 1 is 1 by 36, 1536. Acha, can you see the fonts? Is it visible?
Yes, sir, it is visible.
Okay, great. Okay. And then I went on all the way. I started decreasing the balance steps and I started increasing the number of weighted steps. Okay, here you see all our weighted steps 3 to the power 10, and exponential things, it rose so fast. From 1000 it became 59,000. Okay, and I said, okay, if I tried to generate 37% of a concentration, so suppose you have sample which is water and 100% is sulfuric acid, concentrated sulfuric acid, and you want to generate 37% concentration of sulfuric acid of 37% concentration or dilution, whatever you say. Okay. Now, remember, even if you used balanced dilution, the denominator is 1024, and you won't be able to generate exact 37%. You have to do some maths like 37 by 100 is equal to x by 1024, and you solve x and you get what? 378.88. Obviously, in 10 steps, you cannot generate 378.88. You have the option of generating 378 and 379, because you can generate all the numerators from 1 to 1023. Am I clear? Okay. Now, obviously, 378.88, this 37% is closer towards 379 than 378. So those who are from electrical engineering background or electronics engineering background, we have a term called noise margin. So the noise margin is better on the 379 side. Okay, so what I will do, if somebody wants a 37% concentration and I have a balanced mixer and splitter, I am going to use it for 10 steps and generate a numerator 379. Remember, there will remain a rounding error of 0.12, because 379 minus 378.88, 0.12, which is this. Okay. Now, this is actually different from the question that I faced. What she asked was actually volumetric error. I was splitting and my physical process was not correct, so there was error in the volume. This is not volumetric error. This is an inherent error, inherent rounding error. Because I cannot divide by 100, I am using a binary denominator. So the best I can do is 379 by 1024. Okay, so there is an inherent rounding error already inbuilt in that. Now, what we did the hard work. I mean, we didn't do, the computer did, or maybe Nilina did. So what we did is we found out if we used the closest numerator, and generated in 10 steps the fraction, look, the error, rounding error is going down by leaps and bounds. Note that though we have used the same number of steps in all the alternatives, the error in the target concentration reduces with increasing number of weighted steps, which may be one of the motivations to study the weighted dilution technology. Because we proposed weighted dilution, we were saying that. Now what I did is I plotted from 10:0 to 0:10, and you see the error first rose up, then went down, and it went very low. Okay, you see the error percentage is a few orders down. Okay, at least 2 orders down, 1/100. Also note that just because the denominator came down step by step, the error did not reduce. It first went up, held it for two held it for 2 plots, 8:2. So what I am saying is, if you wanted to have a less error for this particular fraction, not for all fractions, this particular fraction, you should have used 7 balanced steps and 3 weighted steps. Then you got better than all balanced steps. And if you used 6:4, means 6 balanced and 4 weighted steps, you got almost all the advantages. So no use using 10 balanced steps and increasing the cost. Okay, so you always in engineering, you always have a compromise, right? How much you spend and how good you get. The optimal answer for this fraction is 6:4. But obviously I'm not going to just ask you to believe coincidental results. I'm going to give you results for all fractions. Okay. Now, some of you might ask, it is not right to compare things this way, because you can say, here the denominator is so large, here the denominator is so low. How can 10 balanced step compete with 10 weighted step? It's not fair. It's not fair, you can say, because these are all less costly things. These are all right costly things. So these are all much costlier things. So how should you compare actually? Okay, you should compare like this. So it's like this. I am saying, okay, I will go for forgive me for using brands. So I will spend say 10 lakh of rupees for brand 1, and I'm going to spend 30 lakh of rupees for another brand car, and I say, oh, this second one is so good. You will say, no, please spend 25 lakhs for each of them, say for a Suzuki car of 25 lakhs and a Toyota car of 25 lakhs, maybe close, you don't have to be exactly 25 lakhs, and then compare who is better than the other. That will be a much fairer comparison. So I actually go ahead and do that now. I said, okay, let's do this. 6 balanced steps, 2 weighted steps. Denominator is 576. Compare it with 9 balanced steps, 512. Then 5 balanced steps and 3 weighted steps, 864. Compare with it 512, and also compare it with 1024. Then you will say, no, you are always keeping the balanced on the lower side. I said, no, I am comparing with 10 lakh car of Toyota with 10 lakh car of Maruti with an 8 lakh car of Toyota. Okay, something like that. I mean, I am trying to justify myself. Okay, but then also I have noted a few things. If you generate all the fractions with denominator 576, calculate the number of dilution steps of all, divided by 576 to get the arithmetic mean. This is the number of steps. This is the average number of waste droplets, and I calculate, and then average number of droplets of total input sample and buffer. Here you see slightly better values from 7.07 to 6.49 for the balance step. But the actual thing is the waste, okay? And the waste is always more in balanced dilution. Okay, and not with 864 to 512, but here again this 4.78 to 5.02. And what I did is I then put the and the comparison is here. You see this dotted one, this is wastage of weighted dilution. This balanced one is the wastage of balanced dilution, and you see there is a clear difference of 10% waste saving for weighted dilution. Now you say 10% of sulfuric acid don't matter. You don't know whether you have to mix a very costly sample. You have to mix a very costly sample, and maybe it's costly like gold solution or something. I don't know. And then 10% wastage can be substantial. So we are proposing a way to save wastage. We are proposing a way to save wastage. We are proposing a way to save samples and buffers. Okay. Okay. I hope that motivates the usage of weighted dilution. I just plotted as histogram. You see, the balanced case, the weights are these brown ones, and the balance the wastes are these green ones, and for weighted one is these brown ones. And you see, for the browns one, the brown bars are higher on the lower side. Like I found out how many fractions had zero wastage. I found out how many fractions had one wastage, one droplet of wastage. I found out how many fractions had 4 droplets of wastage. Okay, and then I had plotted them. Okay, for 10 this will be 1024. There are 1024 fractions. For 7b, 7 balanced and 2 weighted. Okay, it will be how much for 7 balanced and 2 weighted? It will be maybe 576 into 2. It is slightly higher than 1024. So it is 1152. If you see here, it is 1152, and we have plotted the basically I have plotted the frequency plot, and you see the brown bars are all higher on the lower side, and the balanced ones are all higher or taller on the right side. That means the wastes were much more in balanced side. Okay. Okay. Same thing happened on step count. You see, the green ones are taller on the as the step count increases. Same thing happened on the input sample count. You see, one input sample is required for nearly 275 fractions. Only 2 sample droplets were required for nearly 250 fractions, whereas the green ones, they were lesser on the left side and higher on the right side. Am I making sense? Can I hear some voice? Am I making sense? What I mean by this greens? Greens.
Yes, sir. Yes,
Yeah.
sir. It is understandable.
Okay. Okay. Great. Now again did the same thing, comparison of buffer count, the same result. I put all of them together, and you know, this is like that Gupi Gain Babagain Bhuter Raja Dilo Bor, that dance drama. First for the zamindars, then for the soldiers, then for the Brahmins and fathers, and then at the end all of them together. I don't know. I mean, that's a favorite film for me, so I always keep remembering that. So all of them together, and still you see the greens are high on the right hand side. Okay. Okay. Great. Now I did a very simple plot. You'd know DMRW. DMRW is one there are two very popular balanced dilution techniques. One is DMRW, another is BS. And you see the red ones are the plots for waste, the plot for waste for DMRW, and then green dotted ones is for polarized error in WD. And you see, obviously, if I this figure is not good, I should have drawn an identical green line bottom also with a reflection, but this red is always an envelope for the green, right? So the red is always an envelope for the green. Okay. Okay. And the same thing is for I think I did it for I did it for 2 different fractions. Okay. And just for 2 different fractions I have plotted. Okay. And that finishes the motivation for weighted dilution. I am not going to talk about simulation, the actual program, how it was optimized, how it was made efficient. So this will be more like presentation of the result. The theory for weighted dilution is finished. I can stop here again for 30 seconds or 1 minute if you have any questions. Looks like many have slept. I have bored them. There is no sound.
So there may be another chance that you have explained so clearly that we are understand it very nicely.
Okay, thank you. Uh, as a scientist, I want to believe that, and then as an engineer, I always have doubt about that. Okay, thank you. Okay, so now I'm going to talk about that fraction generation, simulation-based fraction generation by weighted dilution. Now the science part is over. Now comes the engineering part. Okay. Okay. But there are a few combinatorial results here also. I will try to give the proofs, but it is difficult to do it in a single class. It's already 1 hour over. Okay. Now, while generating a particular fraction, we try to minimize one or more of the following criteria, that is, number of total mixing steps, weighted steps, waste droplets, sample droplets, buffer droplets. No present algorithm can do all these simultaneously. It is not possible. All of you understand, right? Someone will be good from the waste point of view, someone will be good from the error point of view, someone will be good from the sample point of view, like that. Okay. Okay, this one I have already shown you already. Okay, but just for the sake of completion, I will just go once more. So you see, 1:1. Sorry, the first step is 2:1. I generated 6/18. These 3 drops means I have generated 3 droplets of 6/18. And then I used 1 droplet here. I used 2 droplets here. That means all the 3 droplets got used. This is very important. Okay. Then I pulled in 1 droplet here. I pulled in 1 droplet here. I generated 2 droplets, as this was a balanced dilution, 1:1. And then I used 1 droplet here. So there was 1 waste. On the other hand, I got 2 droplets here. I got 1 droplet here, mixed that and got all 3 droplets. So finally, I had only 1 wastage. And it is pretty obvious. You see how many samples, how many buffers I use, 2 plus 1, 3, because I am pulling in. You see the direction, the droplets are coming from here to here. So I used 3 samples, I used 1 buffer. So 1 droplet of buffer, I used 4 droplets in all. I got 3 droplets with the target concentration. So the waste droplet is naturally going to be same, and it is as easy as that. There is nothing hidden here. Okay. Okay. But have a look at this. I can go ahead and simulate all the generations. But remember, this is where I need to be careful about. And not only careful, this is actually going to give me lot of alternatives to generate the same fraction. And as I said, I will simultaneously try to optimize many different criteria. The different sequences are going to be of help to me. So let's see, I'm saying let's select 3 steps again. The first one I did here is 2:1. Then I did 1:1. Then I did 1:2. I am saying 1:2 because the smaller concentration is taken as 1, the larger concentration is taken as 2. And this is the convention I'm going to follow throughout my talk. Okay. Then I got 5/16. I had a second case where the first dilution was 1:1, the second dilution was 2:1, the third dilution was 2:1, and I got the same fraction in a different way. So all the mixings and intermediate fractions were different. But this was not a good example for this talk. It could have been a better example. Why I am saying not a good example? In both of these sequences, the number of samples, buffers, and wastes were same. I would rather go for an example which had these values different to show you that such sequences exist. But as I was a student who always prepared at the last moment, I could not uh, draw such a one before the talk anyway. But you have to believe me, there are many. Okay. Now have a look.
Sir,
Now I am going to exactly
one
give
interruption, sir.
yeah,
I have a question. Can you please go back to the previous slide?
this one.
Yes, here, sir.
Yeah, yeah.
Sir, you have mentioned that this is case 1 and this is case 2 with different sequence of mixing of different ratios, right? So is this the way to choose this ratio sequence, or it is case dependent, sir? Case
Yeah,
dependent
yeah,
means
yeah. I
target
will,
dependent.
sure. Very good question. I mean, it's actually a output sensitive question. Means it will depend on. See, what I will do while simulation, I will generate both the ways of generation. Okay, and I will also note how many samples, how many buffers, how many wastes are there. And if the user says that optimize the optimize the number of waste droplets. Okay, then I am going to choose that particular sequence which has lesser waste. Got it?
Okay, sir. Okay, sir.
Okay, because try to understand this. I mean, there can be this confusion. Since I will do an exhaustive simulation, I will have all the sequences generated. I mean, that will be the correctness of my simulation, that all the sequences must get generated. Okay, and from that, I will have an intelligent way of tree pruning such that in minimum time I can go and select the best sequence based on the criteria. Okay, because the user can say this. Okay, first optimize the waste droplets.
Yes, sir.
Then if you have three different sequences for the same fraction, with having the same waste droplet which is say 0, can you optimize the sample over the buffer? You get my point? There are
Yes,
two
sir.
different
Yes, sir.
factions. Okay, and then in simulation we are going to note all of that down and prepare the lookup table in such a way that all the criteria are going to get optimized in exactly the way the user will choose.
Okay, sir.
Okay, that is
Okay,
all
it's
possible
clear.
because
Yes.
because the whole problem size is so small. N is only 10. Okay, the N is only 10, so I can do everything. Okay, but what I wanted to tell you, those who are doing research in microfluidics, please understand that someday the user is going to be very ambitious. They are going to want exactly in this way. When you go to buy a car, or car is a very difficult example. Say you go to buy a shirt, you first say that okay, I am going to buy linen. Then you say okay, I want light color. As soon as the helper in that mall comes up with
Right.
3 light colors, you say no, I don't like this sea green, I want a different green. Okay, so you are optimizing step by step, first
Right, sir.
linen, then color, then texture, and all these things. And
Yes.
customers are always like that. Okay, so
Thank you,
so
sir.
yeah, thank you for the question. Yeah, okay, so you see, now I'm slowly going deep into the number of ways the sequences are getting generated. Okay, now have a look. I have 1 balanced and 2 weighted. 1 balanced and 2 weighted. Have a look. I can say that the first one is balanced. The second one is W1. W1 means 2:1. The third one is W2, means 1:2. So if the first one is balanced, then 0/18 I can generate 9. Then I can do this. Take 0 as 2 and 9 as 1, you generate 3/18. Take 9 as 2 and 18 as 1, you generate 12/18. Again, very simple calculation. Again, very simple calculation. 9 into 2 is 18. 18 plus 18 is 36. 36 divided by 3 is 12. So what did I do? By the time I came here, I had 3 concentrations in my hand, 0, 9 and 18. In between 0 and 9, I generated 1 fraction. In between 9 and 18, I generated 1 fraction using 2:1. Then I say my third step will be 1:2. And then I generate 4 more fractions, 1, 5, 10, 14. So look what happened. By specifying the sequence 1:1 followed by 2:1 followed by 1:2, I could generate how many fractions? 7 fractions, because there are 7 nodes in this complete binary tree of height 2. Okay, so it is of height 2. So it is basically 2 to the power 3 minus 1. Okay, but you know, I have more choice. I could make the first one 1:1. I could make the second one 2:1. I could make the third one 1:2, and I could generate 7 other different fractions. Okay, I could do that. Okay, so let's see. I'm going to come to this lemma a little bit later. I think you are not yet ready. Let's have a look at this. So here also I have balanced weighted. 1:1, first one. Second one can be 1:2 and 2:2 or 2:1. Okay. Now I am drawing a more complicated tree where I am accommodating the first tree that I have shown you on this side. Okay, on this side. Or rather, I will tell how the first tree that I showed you 3 slides back is embedded here. Okay, so you see the first one is 1:1. The second weighted dilution could be 1:2 or 2:1. The third weighted dilution could be 1:2, 2:1, 1:2, 2:1. Okay, and you see this marked, this enclosed thing. This portion of this tree actually entirely contains the first slide that I showed you. Why? Because the first step was 1:1, the second step was 2:1, the third step was 1:2. And you see the 7 fractions I generated: 9, 3, 12, 2, 7, 11, 16. All these 7 fractions are already here. Now, how many fractions got generated in this tree? Have a look. 1 here, 2 plus 2 here, 4, 4 plus 1 is 5. And you see 1, 2, 3, 4, 4 into 4, 16. So 16 plus 4 is 20 plus 1, 21. 21 unique step sequences starting with a balanced dilution. So I could generate 21 unique step sequences. Remember, the fractions are not unique. Here also I got 16, here also I got 16. Here also I got 7, here also I got 7. Got it? Okay. And you see there is a symmetry: 2, 16, 11, 16, 2, 7, 11, 16 here, 2, 7, 11, 16 here, 4, 8, 13, 17 here, and no, it's not exactly same here, but these two means after using the first balance step and then 1:2, then 2:1, here the reverse way, 2:1 and 1:2, they generated the same fractions. But mind you, they are unique way of generation. They are unique way of generation. Anyway, obviously the fractions are not all unique, because the number of unique fractions is only 1 to 17. There are 17. I am saying here 21 unique step sequences starting with B. Note this very carefully, because this is very important for the simulation. Okay. Now, since we are computer scientists, we have always a bad habit of doing maths. Okay. Sometimes when it is required and sometimes when it is not required. I don't know, a few of my mathematics colleagues also might have joined. They will appreciate. We have a tendency to do maths. Okay. Anyway, because why? It's sometimes for intellectual satisfaction without any use. Okay. But I am also of that type. Now, so what I did is I wanted to see how big is this simulation, how much this simulation has to work, what is the number of nodes it has to expand. Okay, so I did this maths. I said for a maximum of B balanced steps and W weighted steps, The upper bound on the total number of ways to generate fractions is given by b plus w choose w into 2 to the power w into 2 to the power b plus w minus 1. Don't get psyched with three parts. I will explain exactly how it is going. Okay? Okay. Let's have a look. What did I say? I said the the steps I can choose in this way: balanced, weighted, weighted. I could have chosen weighted, balanced, weighted, right? Or I could have chosen weighted, 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 balanced, right? So there are three ways depending on where the B is. Okay, and mind you, each of these W could be W1 or W2. So let's have a look at this small combinatorial calculation. Number of ways to write B number of capital B's and W number of W's. See, the problem is like this. You have 6 steps. The first 2 are balanced, the next 2 are weighted, then a balanced, then a weighted. Does it make you remember the problem you first solved in class 11 combinatorics, permutation combination? Number of ways to write this word. This is not an English word, which has 3 B's and 3 W's. It would be factorial 6 divided by factorial 3 into factorial 3, right? So I wrote b plus w factorial divided by factorial b into factorial w, which is combination of b plus w comma w, means b plus w choose w. Each of these w's could be w1 or w2, means 1:2 or 2:1. So the number of ways of writing these w's is 2 to the power w. These two are the easy part. The third part is slightly not difficult, just slightly involved. I have to change slide. I am going to tell. Note that each of the above C b plus w comma w into 2 to the power w cases correspond to a tree like this of height 2 to the power b plus w minus 1. Okay. So you have this tree. Okay. So I'm sorry. I think I am wrong. I'm wrong. It is, that is not the height. The height is basically b plus w minus 1. Okay, b plus w minus 1. You see, b plus w here was 1 plus 2, 3, and the height is 2. So that's a small mistake. Please forgive me for that. So it finally gets multiplied by the total number of nodes in a complete binary tree of height b plus w minus 1, which is 2 to the power b plus w minus 1 plus 1. I showed all the steps because, you know, I mean, in online calculation it becomes difficult to draw figures. So it is 2 to the power b plus w minus 1. You can check it with this small tree again. b is 1. There is only one b. W is 2. So it is 2 to the power 1 plus 2, which is 2 to the power 3, 8 minus 1. All of you know that the number of nodes in a binary, complete binary tree of height 2 is 1 plus 2 plus 4, which is 7. Okay. Okay. So basically for b equal to 1 and w equal to 2, it gives 3 into 4 into 7. 3 because 3 choose 2 is 3. 4 because 2 to the power 2 is 4, w is 2. 7 because 2 to the power 3 minus 1 is 7. So 84 ways. Now this is the maximum side, means the number of fractions, the number of ways fractions can be generated is bounded by 84, or it is bounded by this big number if b is equal to b and number of w's is w. Actually, the number of step sequences is much less. It is less by a factor of 2. It is nearly half of this, or a little bit more than half. Why is that? I am going to show you. I am talking about uniqueness of fractions sequence and uniqueness of sequence of generation. You know, I already said that the denominator is 18. So the number of unique numerators is 0 and 18, which is 17 unique numerators, and it is far less than 84, right? It is far less than 84. So there must be duplication. but all duplicates are not useless. I already told you that some duplicate sequences may be useful because I am trying to optimize something else. Okay, so if you have 2 to 3 alternative sequence of generating the same fraction, one may be better than the other on the basis of the criterion that is being optimized. However, in the above counting method, some sequences are also duplicate. Now this is a little bit finer point. What I am saying, like in BW1 W2 and BW1 W1, you understand, right? What is BW1 W2 and BW1 W1 means the first two steps are same, the third step is different. The fractions generated at level 0 and level 1 cannot be different, which leads to the need for lemma 2. So what I am saying is, what did I do? I said for each fraction, for each number of sequence, each number of thing, I multiplied everything by 7. But try to understand, if the first step is 1 by 2, the second step is 1 by 2, sorry, the first step is 1 is to 1, second is 1 is to 2, the third one is 2 is to 1. On the other hand, if the first one is 1 is to 1, second one is 1 is to 2, and third one is 1 is to 2, look, the fraction that was generated at this level by only 2 steps is the same, right? So I did not generate a new step sequence. Okay, I should not multiply with, I should not blindly multiply all those 3 terms. Okay, here also the fraction generated in the sequences from going from here to here and here to here, in the first 2 steps, if I stop here, I get the same fraction, right? Okay, so this gives me a requirement for lemma 2. Okay, so I'm saying the actual number of it is slightly less. Okay, this is what I am saying. I counted the unique step sequences in each of these cases. BWW, it is 21. This is starting with 2 is to 1. Then the second step can be B or W. The third step can also be B or W. And in all these ways, I got 23 unique sequences. I have noted down all of them. You can go through them later. And here also, the first step was this one. The first step was 2 is to 1. Here the first step was 1 is to 2. And I have a mirror result. Again, I got 23 unique step sequences. And if I add them, 23 plus 23 is 46, plus 21 is 67. So I actually have 67 unique sequences, which is obviously less than 84, which was the maximum number of sequences possible. And I give here a rough lower bound. Though those of you who are interested in mathematics, you can actually go and calculate the exact number of possible unique sequences. It is not difficult. Okay, but since I was doing a bounding, I was happy with a lower bound which is half of this. And what did I do? I said, note that at least all the fractions at the leaf level are unique, and there are some more at the other level. So what I am saying is, look at all these 2, 8, 13, 16 at this level, 4, 10, 14, 17. Now all these, the sequences required were unique. Okay, because somewhere it is going to differ, right? In the 3 steps, you can say again, sir, just now you said the fraction is same, here 13, here 13. Remember, I am not talking about the uniqueness of numerator. I am talking about the uniqueness of the step sequence. The first one here is 1 is to 2, then 1 is to 1, then 2 is to 1. The first one here is 1 is to 2, then 2 is to 1, then 1 is to 1. So the way this fraction was generated, the same fraction was different, and who knows how many were the waste, how many were the samples used, and how many were the buffers used. They may be all different. Okay, so they are unique things that we need to tackle. Okay, and then I made a simple lemma which I have already shown you before. It is, have a look. A lower bound on the number of ways the fractions can be generated is given by b plus 1 w by w. This is same. This 2 to the power w is same. The third one is simple. It is the number of nodes at the leaf level. which is all of you know, if the height of the tree is 2, then there will be 2 to the power 4. If the height of the tree is k, then it will be 2 to the power k. Since the height of the tree is b plus w minus 1, the number of nodes at the bottom level is 2 to the power b plus w minus 1. And if you again calculate this for b equal to 1 and w equal to 2, you get a number which is less than 67. Obviously it has to bound 67. Okay, and let me see what it is. 2 to the power b plus w minus 1 will be 2 to the power 4, which is sorry, not 2 to the power 4, 2 to the power 2, which is 4. So it will be 3 into 4, 12 into 4 will be 48. And 67, which was the unique number of sequences, lies between 48 and 84. And 48 is somewhat little more than half of 84. So what I was saying is the lower bound is about half of the higher bound. Okay, maybe I bored you with too much of maths. There will be no more maths in this talk. Rest are only results. Okay, so I assure you for that. Okay, now have a look. This is selection of optimal mixed split sequence in involving WD. I showed you how to generate the target numerator of 2 and the denominator is 18. Okay, there are 7 different ways of generating just the fraction 2. Some of them use only 2 steps and some of them use 3 steps. Now, not always you will be lucky that a fraction will be generated in 2 steps. Most of them will require all 3 steps, and there you will actually have a level playing ground in comparing the waste. If you have a look, there are 2 steps and the minimum waste is 2. Sorry, the number of wastage is 2, the number of sample droplets is 1, the number of buffer droplets is 4. And obviously you are going to use this particular sequence for generating the fraction 2 because here the number of steps is minimized. So it will take less time, it will take less energy, and if the number of steps is less, I will obviously go for it. But you see, there are so many different ways of generating the same fraction. None of your existing microfluidics algorithm will tell you all that. Okay, and then you can actually choose from them which is using minimum waste or which is using minimum sample or which is using minimum buffer. Okay, so just let's have a quick reading. What is it saying? Target 2 is obtained by 7 different step sequences. And our goal is to get the optimal step, that is minimum number of steps to generate 2. In addition, optimum step should have minimum number of waste droplets, minimum number of weighted steps, minimum number of input sample and buffer droplets. So I'm saying your number of steps may be same in 2 different sequences, but out of that, if you have 3 balanced and 1 weighted, in the other if you have 2 balanced and 2 weighted, then obviously you will go for 3 balanced and 1 weighted because that will be having less cost. Okay, I have noted down for all the step sequences for generating fractions from 1 to 17. You see some of them require only 2 steps. Obviously, if you are generating fraction 6, numerator 6 and numerator 12, you need only 1 step. And a few require 3 steps. Okay. Obviously, when you generate 10 steps, there will be many more fractions and these are going to be much complicated tables, which I cannot show you here. Now, obviously, I didn't store here alternate sequences. Okay, I did not show here alternate sequences. I just showed you one particular sequence and what are the number of steps, number of weighted steps, number of waste, number of input sample, number of buffer. But there actually exists number of different sequences where different sequences are better for different optimization criteria. And if you are doing a simulation and storing them in a lookup table, you have to take care of all that because you don't want to miss any sequence that is better from some other criteria. Okay. So I'm going to tell all those results. First, let's go for the time. Number of balanced steps is 1, number of weighted steps is 2, total step is 3, denominator 18. upper bound 84, number of nodes you have to visit, lower bound 48. Actually, the number of ways to generate optimal fractions, I will tell you about this. Please hold on. What is the number of ways to generate optimal fractions? You see the timing, it generates in no time. We have gone up to see number of balanced steps is 9, number of weighted steps is 3. It is already more than the state of the art, because all of you have seen the state of the art is you go for a denominator of 10. You go for a denominator of 10. You generally go for 10 balanced steps. Okay. We have gone up to 12 here. Okay. See, till this point, look at the 7th row. It's only taking 2 minutes, which is nothing. Remember, this is only a pre-processing step, which you will just generate once to generate all the sequence in your lab. That in the actual chip, there will be only lookup table containing how to generate the generated sequences. There will be only lookup table. This is not going to happen during actual generation of the fractions. Okay. So this is only one pre-processing time, which is nothing, because in your computer, in a server, this will just get generated in a few microseconds. Okay. See how the time is rising. The only non-trivial time here is 4 weighted steps here, and then 4 weighted steps here. You see 49 minutes. 12 balanced and 2 weighted steps is still 4 minutes. Obviously, the complexity increases much more with weighted steps. But if you restrict it to only 2 weighted steps, simulation is cakewalk. In a very, very casual laptop of my PhD student with 4 GB RAM, I don't know, the times were like this. And that has to be run just once in your life for pre-processing. So what I am saying, this is extremely fast simulation. You don't have to worry about the timing of simulation. Now the second thing I will say, look, the denominator is 18. So the number of unique fractions is 0 to 17. The number of sequences I am storing is only 17. That means for generating each of these fractions, there is only one best sequence, and I am just storing that. But look the difference between these two numbers as we go down this table. When there are 4 balanced steps, 2 weighted steps. 4 balanced step means 2 to the power 4 is 16. 2 to the power 2 is 9. 9 into 16 is 144. Okay. You see the number of sequences I am storing is 161. What does it mean? Means for some fractions I have stored 2 different sequences or 3 different sequences, such that each of these sequences are better from the other based on the user chosen criteria of which is better for number of steps, which is better for number of samples, which is better for number of buffers. Because in some places the sample can be costlier, in some places the buffer can be costlier. You may be using very pure water, you don't know, you may have used very, very pure water and the buffer is actually costlier. Okay. Okay. Now have a look how this is growing. Obviously, as the numbers are growing here, it is showing that weighted dilution and simulation is something for the future. Why? Because there are different sequences optimizing different criteria. But we are also worried how much space will be required on the chip for the lookup table, right? So you see it's not much. For a denominator of 36,864, the number of unique fractions is 36,863. We have to store only 52,000. So it is between the average number of sequences that you have to store for each fraction is within 1.5. 3 into 18 is 54, and this is 52. So on an average, 1.5 sequences get stored per fraction, and that is going to give me the way to optimize all different ways of criteria, all different ways of choosing the criteria. Okay, that finishes the weighted dilution presentation. These are the few publications that were generated from this research. We had the first one in applied algorithms. Then we had a select bio. This is a very, this is more on the biology side, so mostly the famous doctors of India, they attend this conference. And the third one is a journal paper in IET Computers and Digital Techniques. Um, the unfortunate part is we were the first to give the idea of lookup table. We also have a patent, but our paper was refused from IEEE transactions, and we see after 1 year there is a lookup table based work in IEEE transaction. But never mind, you may have, all of you may be doing research from on the right topic from a difficult place, which is the eastern part of India, but it's okay. Okay, it's for the fun of research. It's for the fun of research. We do research, not much for the results. Okay, okay. Um, this is where my weighted dilution ends. I can stop here for 30 seconds. Um, next is SIMUP, which is use of simulation for balanced dilution, which probably you will understand very easily because I have done all the hard part with weighted dilution. We can stop here for questions. Okay. I just stopped the sharing. If some of you have any questions, if you please switch on the video, and then I can answer your question if anybody has any question.
Good afternoon, sir. I can't switch on my video as I am on desktop. I have a question that if for a particular concentration factor we can have multiple sequences,
Right.
can there be any such sequence which is better than any other sequence in all terms, that is in terms of all the optimization factors?
Yeah, it's possible. Yeah,
And so in
it's
that
possible
case,
because
yes, sir.
yeah.
If it is possible, so in that case, can we have a further pruning using the domination criteria?
Tell me, just I didn't get your last line.
Yes, the domination criteria, if any of the sequence is better than another sequence, another unique sequence in terms of all the optimization parameters, in that case, will the pruning regarding domination criteria will work?
Oh, okay. I think yeah. I didn't explain you the consideration. Mind you, whatever we are doing, this simulation is not during actual generation time. Okay, so we are doing the simulation for generating the sequences. When you will actually generate on the biochip, you will have the exact sequence stored there. Okay, that you do 1:1, then 2:1 between these two fractions, then 1:2. So all you will be doing is seeing the lookup table. You will just generate. Okay, now what you are saying, unless I generate all the ways of generating a particular fraction, say 2, how will I know that it is the one is better than all the other? Okay, so I actually during simulation will generate all the possible sequences, and then I can easily choose which is the best one. Okay.
Okay.
Acha, can you see my slide? Shall I go to the slide back once more?
Yes, sir. It's visible.
Okay. So
Thank you, sir.
have a look here, which I was saying. Have a look here. This is not a good example. I should have got an example where there were whether the fraction cannot be generated with 2 steps. But still, have a look. You see, I have generated all the ways to generate fraction 2, because you see in the just a sec. Because you see in the last value here in all these sequences is 2. Okay, and out of this you see this particular sequence is better than everybody else because it had the minimum number of waste is 2.
Yes,
There is
sir.
nowhere here 2. The minimum number of steps is 2. The minimum number of inputs is 1. Likewise, there are other fractions also where you have to store only one sequence, which is better than all other sequences from all point of view. But there are many other fractions where there isn't a single one which is better than every other in one criteria. For them, we will store 2 to 3 different fractions, which during runtime based on the user choice of the fraction and the choice of the optimization criteria, we are going to choose that particular sequence and give the result. Am I clear?
Yes, sir. Thank you, sir.
Okay. If there is no more questions, I will go ahead with using the same simulation for weighted balance steps. Can Dr. Banerjee tell me how much time I shall go for, or should I end here?
Sir, since this is a very interesting one, please continue, sir.
Okay, so let's agree. I should not go, I think, more than 2 hours. So maybe there is 22 minutes. I will take another 15 minutes and then stop for a question answer session. Okay.
Okay, sir.
Now, once we did this weighted dilution, we thought, okay, as we are proposing weighted dilution, and there is one factor that weighted dilution may have a higher cost in terms of technology. So obviously, all the reviewers were asking that you are going for weighted dilution. Can you do it in? Can you really generate a chip with that right now? But not always the theory goes hand in hand with implementation. Okay, it's not possible, because in the history of mankind, always the theoretical works were done much before they were implemented, sometimes centuries before, right? So in our case, maybe we came up with the result 5 or 10 years before the technology which will actually arrive, or maybe it can take more time or less time, I don't know. I am not a technology person from this domain, okay, but we still did the work. And then we thought that, okay, let's see, if I go and use simulation for just balance dilution and compare it against each of these algorithms, we should still get we should still have a takeaway, right? We should still have a value addition, right? So this is what we did. In droplet-based microfluidic domain, the two pioneering algorithms are sample dilution, or BS, and DMRW. We started comparing our simulation result with each of them, and we got very encouraging result. Okay, so for obtaining a target concentration, all of them deploy a sequence of 1:1 balanced mixed steps, but none of them can guarantee optimality. In current lab experiments, a maximum of 10 mixed split operations are used. New idea, again I am saying the same thing, since the number of steps is very small, why not try a simulation guided procedure to get the optimal way for achieving each target concentration? As expected, our simulation generates a relatively larger set of intermediate sequences by trying different ways compared to earlier algorithms. However, we named this one is SIMOP, simulation based optimization. SIMOP uses some intelligence to avoid redundant checks. In real time, SIMOP generates sequences to optimize multiple factors using up to 11 1:1 mixed splits. That is, achieves better resolution than present state of the art. So I said, okay, I mean, my simulation can go up to 11 steps or 12 steps also. It doesn't take much time. Okay. Okay. So you see, let me now give a very, maybe I should have given this at the beginning of my talk, because this is more for those people who are not from microfluidics. Actually, I'm telling how you generate a fraction 799 by 1024 using the BS method, bit scanning. So the idea is very simple. You convert into a binary equivalent. So 799 by 1024, it's a fraction. You convert it into a binary fraction, and you see this 1100011111. It's written here 1100011111, and just the way these ones and zeros are, you actually pull the sample or the buffer. So if it is 1 here, you pull the sample. For all these things, you are pulling the sample. If you is 0 here, you are actually pulling the buffer. And again, I tell you very simple thing. You started with the buffer 0 concentration, sample concentration 1, mix them, got 500 by 12 by 1024 means half. Then you mixed this 512 by 1024 with one droplet of the sample. and you got 768 by 1024. Okay, and so this is basically 3 by 4 actually. Okay, and in this way you go ahead and ultimately you get 799 by 1024. Have a look how many droplets got wasted. You see, in each step bit scanning, one droplet get wasted. Okay, because every time you mix there are two droplets, one is being used and one is wasted. Okay, so in 11 droplets that you used, you got 2 at the end and 9 droplets got wasted. So you see, sample droplets uses 7, buffer is 4, waste droplets is 9. Now let's go to DMW. This is more like a binary search. So if you are thinking about generating 79, the first time you mixed you got 512. Now 799 is closer to 1024 compared to 512. So you do again 512 plus 1024 and then split it. That means you take one droplet of 512, you take one droplet of 1024, mix them and split them, you get this. Then again, since 799 is between 768 and 1024, again like binary search, you get 896. This time 799 is between 768 and 896. So you will use these two instead of pulling a sample, pulling a buffer or pulling a sample. Okay. And this way it goes on. In this way it goes on. And you get 799. And if you see how many wastages was made, the black ones are wastage. So 1, 2, 3, 4, 5, 6, 7. Less than DMRW, less than BS, right? So number of waste droplets is 7. Number of sample droplets is 7. How? Look at here how many you pulled. Here you pulled 2. Here you pulled 4. Here you pulled 1. You say, how come this is 4? Why? Because you have used 4 droplets of this type, right? So you must have pulled 4 from here and sorry, you have used 1 plus 2, 3, 3 plus 3, 6, 6 plus 1, 8. So you need to create 4. So you take 4 droplets of this, 4 droplets of this and make 8 droplets. Obviously not all together. You did it 1 plus 1, 2 and then 2 you are used, then 1 plus 1, 2 used like that. Okay, in actual electrodes, they were made like that. But note at these parameters. Number of waste is 7, number of sample is 7, number of buffer is 2. And you see it is distinctly different from the previous one, right? So immediately the question comes, can there be some other way of generating 799 which will take much less sample, much less buffer or much less waste? Obviously that question will come, right? And this is our generation. Number of waste droplets is 2. Number of sample droplets is 3. Number of buffer droplets is 1. Don't ask me what is the philosophy, because it is got by simulation, right? We kept on mixing fractions and try to see what is better. It's very difficult to track who gets mixed with what, but the end result is this. Do you think if a user has this result, he is supposed to use any of the previous algorithms? An user who is output sensitive, an user who is very careful about the cost, and mind you, there is no weighted dilution here. All are balanced dilution. So you will say that what is the elegance here? You used simulation. Well, when you use computer to play chess against Kasparov, it obviously does simulation, right? And then it goes ahead and beat Kasparov, and then we are afraid that someday artificial intelligence will take over mankind. But still it is going on, and it is going on in an exhaustive way, because God has not given the computer a brain like us, okay? But who knows, in your brain there may be an exhaustive simulation happening in the neurons, right? So when you are saying, okay, I am only taking 3 finite steps to solve this problem, in your brain the neurons may be still doing exhaustive simulation, right? Okay. Anyway, this is going into philosophy, and I actually want to talk less philosophy. Let me
Sir,
finish.
just one thing.
Yeah.
Here, when you are doing the simulation, you are doing exhaustively for all.
Yeah, I am doing exhaustively for all, but I'm not doing it blindly. I am optimizing in between to make the simulation fast. Whatever trees which are useless, I am pruning that. I am stopping expanding there. I am only storing the fruitful simulations and comparing against my previous result. And if I get a new sequence, which Piali was asking, that is my answer. If I getting a new sequence and I see that it is worse than all the previous sequences stored for that fraction, I am going to forget that simulation. I am going to forget that sequence. I am going to drop it. Okay.
Okay.
If only a new sequence is better than the all the previous sequences in some way, then only I am going to store it. Okay. Okay.
And what is the maximum time that is taken for any the largest simulation?
Yeah. Did you see that in that weighted simulation I have reported all the times?
Yes, so I
And
missed
I'm
out
going
the
to do, yeah,
maximum time.
yeah, I'm going to do that again for this balanced solution in my last slide. Okay, that's the
Okay,
end result.
okay,
Okay,
okay.
okay, okay, great. So it's in the order of minutes, not more than that. Okay. And mind you, it is a pre-processing step, so nobody is going to put that on the chip. That is going to be done once on your computer while generating the chip. All you are going to store in the chip is a memory of lookup table. And 1024 sequences into say 3 or into say 2 sequences means you need a memory space of storing sequences for 2000. It is nothing in today's technology in terms of memory that we generate. Okay, it's nothing. Okay. Okay.
Yes, yes, I agree. Yeah.
Okay. So I mean, as I said, I'm from the industry, so I sometimes keep thinking like the industry. Okay. Okay. So solution methodology, how to generate fractions different from BS and DMRW. CMOP takes a single input, maximum number. Okay. I think it's no point going through this in details. You can read the papers. I am going to go a little bit fast. So this is the way. So as I said, whenever a new concentration is generated, we involve CN in a mixed split operation with each of the previously generated concentrations. মানে বুঝতে পারছো, it's like this. Suppose I had 0 and 8. I got 0, 4, 8 in this first step. Okay. Now I got 4, so I will mix it with 0 and get 2, and I will mix 4 with 8, I will get 6. In the next step I get 0 plus 4 equal to 2. Now I am going to do this. I am going to involve this 2 with 0. I am going to involve this 2 with 4. I am going to involve this 2 with 8. So the simulation is proceeding this way. I got a new fraction in this step 6. I am going to use, so 6 is bold here. Okay. I'm going to play it against with 0, 4 and 8 and see what is the fraction generated. And you see all unique fractions have generated in this step 1, 3, 5, but this 5 is same as this 5. But as I said, I have to compare the sequences and see if somebody has less waste, somebody has less buffer, somebody has less sample, somebody has I mean, we are doing that. We are also going to compare that in terms of error possibility. Okay, that is the future work that we are doing. Okay, so I guess you got how am I proceeding with the simulation, right? So you have to keep track of, see, 0 and 8. 0 and 8 are old concentration. 4 is the last concentration. Okay. Then 2 is the newly made concentration, and concentration found till now P shown in bold being the latest one. So in this way I keep, so just the way I have drawn this diagram, the program actually proceeds exactly in this way. Okay, program exactly proceeds in this way, cutting away, as I said, once I compare, if I find that a new sequence is worse than all its previous sequences, all the previous sequences for that fraction, then I don't proceed with that branch of the tree. I mean, common simulation techniques, those who have worked in simulation, they know how to do that. Okay. Now have a look at this. 0 and 8 I got 4. 4 and 0 I mixed, I got 2. Then 2 and 4 I got 3. Okay, have a look here. 0 and 8 4, 4 and 8 6, 6 and 0 3. I got the same fraction in the same number of steps, but you see here I used one sample, wastage is 1. Here I used 2 samples, wastage is 2. So what will happen? If I generate first this sequence, I will store it. When I generate this sequence, I see it is worse than the previous one in all types of way. So I am going to drop this fraction and do not proceed with that branch of tree any further. Okay. But if I generated this fraction before this, then what I am going to do? I am going to go and strike out this sequence and put this one there. I mean, simple program for generating minimum of n numbers, right? If you get a new minimum, you replace the old one with this. If you get a minimum which is less than the previous, more than the previous minimum, you drop it. You don't change it. Just that idea. Okay. This is repetition. While computing the best possible route to each concentration, we aim to minimize 4 different factors and also a mixed one. The user has to only say which one out of this is you give maximum preference. So somebody says I give 1 the maximum preference, then 3, then 2, then 4. So I'm going to run my simulation that way. Okay. Okay, now let's slowly go into the result. I think I have talked a lot. I have again repeated here, whenever a new fraction is generated, we compare it against the present optimal sequences stored in the output data store. Question is how to generate SIMOPS. Okay. This is an example where I generate 313 by 1024 in 3 different ways. Okay, and look, waste is 3 in all of them. These 2 sample is 1, buffer is 4. In these 2 sample is 2, buffer is 3. So suppose you are using a costly buffer, you would prefer to go in this way. Suppose buffer doesn't matter, you can use either of them. And in such a case, I am going to store only one method, not both. Okay, I am going to store any one row. Ties are resolved arbitrarily. Again, you see generation of fractions 313. I have shown that same thing in the, because it is difficult to follow these sequences, I have shown how it got generated. Okay. Now, very soon I am going to go into the results. Again, I wrote the same thing in a different form. Okay, so if you want to optimize the buffer, you should not use this. But if you want to optimize the buffer, you should use this. Oh, sorry, this one is little different. I'm sorry. This is the result for bit scanning, waste, sample, buffer. This is the waste for DMRW, which is much better in terms of error, but you see, it's still using 7 waste, 3 droplets, 6 droplets. In SIMOP, I will have 2 different sequences. One that optimizes the sample and the one that optimizes the buffer, because I am using only 3. Okay. significant percentage of savings in waste generation and sample used in CMOP. Again, this is another example of 511. I am just trying to show that in different fractions we are better. Obviously we are supposed to be better because we are doing simulation, but how better is the point? If we are getting very little, uh, savings, then there is no point doing so much simulation. Okay, but actually the savings are quite substantial. This is storage management. I said let's skip this. This is much more complicated. Let's compare CMOP and BS. Okay, have a look. Waste sample buffer. Okay, waste sample buffer. What did I say? Look at here. In only how many, so this is the frequency. I am saying in how many fractions CMOP and BS uses the same number of waste sample and buffer droplets, only for these few fractions. Okay, say around 52 or 53. In all these fractions, the number, the CMOP uses one less wastage, one less sample, one less buffer. In all these fractions, the number is 354. CMOP uses 6 droplets less in wastage. Okay, 6 droplets less in wastage. Think about the saving. Okay, so that is the saving with respect to BS for CMOP. I mean, there are different ways of visualizing this diagram. This is the way Nilina preferred to show it, but you see it is significant. Only in this small number of fractions, BS and CMOP are comparable. That means BS is optimal only in these few fractions in terms of waste sample or buffer. For everything else, there are better sequences than BS. Same thing for DMRW. Same result for DMRW. DMRW is much better than BS in terms of optimizing waste sample and buffer, because you see a large number of fractions are here at the same site, but there is still a large number of fractions which are getting optimized, okay, which you cannot get if you use DMRW. These are again different ways of showing that CMOP, how much savings you can get, if you use CMOP over BS and DMRW. Okay, so that motivated the use of simulation. The fractions that are currently considered in the present day labs is 10, whereas we went up to 11. Now somebody was speaking about time. This is where it is. See, for a fraction of 2 to the power 10, 1024, we need 10 minutes of simulation time. We need 10 minutes of simulation time in a very, very, very normal laptop with 4 GB of RAM. Okay, if you run it on a server, maybe you will get 1 or 2 minutes. When we went up to 2 to the power 11, we needed 2 hours, 3 minutes, 36 seconds. But still, you know, running the simulation once in the lab before generating the chip, 2 hours is very much possible. Okay. Okay.
Why you have restricted it to 11 only?
Oh, because, you know, I mean, when you generate the sample, you don't go beyond a fraction of 1024. Okay, you know, because if you are using, I mean, think about the error. You see, you are generating 37% and the error was 0.12 divided by 1024. That's a very low error, right?
Yeah.
Means, you know, when we were talking initially, there may be volumetric error. When you are actually separating, there may be volumetric error more than that. So the rounding error doesn't need to be more than that. So using 10 steps is more than enough. And I have gone up to 11 steps, looking at the future for the next 5 years. Okay?
I see, sir.
Okay, and these are all side results where you don't really need to see. What I said is, when I did CMOP, I found that for all these fractions, the optimal sequences were very symmetrical. So I said that what I meant is that if you are generating a fractions, say 91, the sequence is exactly mirror image for generating the fraction for 1023 minus 91. So these are side result which we probably be able to use somewhere later. Maybe one sequence can be stored in the lookup table, then the other can be derived from that lookup table. So the number of sequences I will need to store in the lookup table can be halved. Okay, this is the idea. These are some ideas of optimization for future. Again, let's let's keep this. I have already said these are the two publications that we had, and in this work I had three BTech students who also worked with us. One of them is now working with Yahoo Japan after having having an MS from IIT Bombay, and the other two have followed up MBS, not followed their their research in microfluidics, but anyway. And that's it. Thank you. Thank you for patient hearing.
Thank you, Dr. Majumdar, for your nice informative talk. The way you have covered the weighted mixing, it's very nice, and explanation was very interesting. I believe many of us will definitely want to use this method in future of the microfluidic research work. Thanks a lot. And now, if there is any question from our participants, please ask.
I just have one question. I wanted to ask, what platform you have used? I mean, what programming language you people have used for this?
Oh, I think she used Java. She used Java in just a Windows based.
Okay.
Yeah, I mean, if I use C, I mean, she was comfortable with Java. She used it. I hardly know any programming language. I'm the HOD of computer science. I forgot everything. I would have used C because that is one which I'm comfortable, and in C it would have run much faster.
I see.
Okay, the last thing I say is you might think that the way I presented it means that we can throw away all the microfluidics algorithms and just use this. In a way it is, but I will tell you where is the difference. You see, there are two things. One is you can have art where somebody is drawing, okay? Somebody is doing a sketch, somebody is doing a oil painting. And my one is like photography, okay, which came in 20th century. But the need of fine art has not lost his significance. But more and more people are taking towards animation. The way the anime things are working. The Japanese animation. My daughter always sees all those films. Okay, the way they are improving. Very soon, we would not need any hero or heroines. I mean, all of them are so good looking, and everything is so nice. I mean, everything is so human like. I mean, it is very difficult to compete with them. I mean, I am worried about the Bollywood heroes, and Bollywood heroines. Okay, so that is it. The other way I can see is you can use our simulation is when the cricketers practice, they use a machine for throwing balls, right? They use a machine for throwing balls, okay? And they simulate Muttiah Muralitharan's ball, and then they simulate Andrew Flintop's bowling, and they simulate, I don't know whether they can simulate
Shane
Lassie.
Warne, maybe.
So,
Maybe Shane Warne's. Yeah.
yeah, so and how it is helpful, how it is helpful, because the bowling machines do not get tired. Okay, they keep on bowling for 2 hours. Okay, you cannot have Muralitharan for giving practice to an Indian player, right? But the bowling machine can. So what you can do is tomorrow you get a very new efficient algorithm. You can test it against my simulation result. You can test it against a SIMOP, how good you are. So we are actually setting the benchmark. Okay, that's it. Thank you.
Thank you so much, sir. So now I would like to request Dr. Kamalika Datta, Associate Professor of our Department Computer Science and Engineering, JIS University, to felicitate our speaker, Dr. Shubhashish Majumdar, sir.
Firstly, thank you, Dr. Banerjee, Firstly, many thanks to Professor Shubhashish Majumdar for delivering such a fascinating and super engaging talk for the post-lunch session. It was a very powerful talk. We were actually able to grasp many of the things, but you were asking like why we were not asking questions so much, because it also takes some time to, sink in the details within ourselves, and then
Right.
we understand the topic slowly and then we move on. So, as a token of appreciation from GIS University, we would like to present you this particular token from GIS University. Is it visible to you, sir?
Yeah, it's very much visible. It's nice.
Yes, thank you. And also this memento, e-memento for you. But we also hope that if our student and if we want to interact with you for some topics or the other, you should be available for us in future.
The trouble is time, I keep getting phone calls, so many. I mean, nowadays I hardly have any time for research, and it's my PhD scholars are the most who suffer. Anyway, okay, but
Okay,
thank
sir.
you for the thank you
Thank you. Thank you,
for
sir.
giving such an offer.
Thank you, sir. Thank you so much for your help here.
Thank you. So may I
Thank you,
leave? Yeah,
Dr. Datta. And also, once again, I want to say thanks to our speaker, Dr. Shubhashish Majumdar, sir. Thank you, sir.
thank you. Bye.
Thank you, sir.
Thank you, sir.
So we are meeting tomorrow again, Dr.
Yes,
Banerjee?
yes. And I would like to share the form. I guess you have already shared the feedback form
Form,
link to
but
our all
it is
participants.
better that we share it here. If somebody
Okay,
has missed it out, they
fine.
can
So
fill it
let
up.
us take it once again. And
And just one more thing I wanted to add to the participants that please enjoy the last day of this talk, because last day we have three very, very strong talks on Memristors, which is again an emerging topic, and where you will be able to see that how we have moved again from, from your small scale designs to chips. The same way how microfluidics have gone, and now we have quantum computers where people thought of quantum algorithms, they are putting that in. So I hope you will be enjoying our session tomorrow as well. Please join us at 10 o'clock tomorrow. Thank you very much. Over to Dr. Banerjee.
so this is all for today. Hopefully, you have enjoyed a lot. And tomorrow we are going to meet on our last day of this FDP, and definitely will enjoy another 3 interesting sessions. Thank you, everyone.